All right. So after the racket hits the ball now has potential energy. So the equation, there's two types of potential energies. There's potential energy due to gravity and potential energy due to a spring. So for potential energy due to gravity, you have U, G is equal to M, G, H. So the UG stands for the potential energy due to gravity, and then the M is for mass, G is for gravity, H is for the height of the object. Now for the potential energy due to a spring, you have U, S is equal to 1 half K X squared. US being the potential energy due to spring, the K being the spring constant, and the X being the displacement due to gravity, due to the spring. All right, so when the ball is moving, so after it's made contact with the racket, it now has kinetic energy. So the equation for that, we have K for kinetic energy is equal to 1 half M for mass, V for velocity, and that's squared. So this one's just kind of self-explanatory. When it's moving, it has kinetic energy. All right, so now I'm going to talk about the law of conservation of energy. So the law of conservation of energy states that energy cannot be created nor destroyed, only transformed. So this can be expressed through the equation EI is equal to EF. And this just says that the energy initially is equal to the energy final. So it's just transferred. This can be broken down into U initial, which is potential energy, plus K initial, which is kinetic energy, is equal to U finally plus K final. And this is just kind of the equation that we end up using for the EI equals EF, just broken down. And so then we move on to the non-conservative forces. And the non-conservative forces is just focusing on that transformed part of the law of conservation of energy. So, as I said, the law of conservation of energy cannot be created nor destroyed, only transformed. And this focuses on the transformation of energy into heat, which makes it lose energy in the system. And so we get the equation FD, which we often use force friction for this, FD cosine theta is equal to change in U plus change in K. And so this change in U plus change in K is going back to our law of conservation of energy. As you can see, it's very similar. But then we add in this FD cosine theta part. And this is the force of the friction, and this is the angle that it's being applied at. So then that's where the energy is being transformed and where it's going to be lost. So I'm going to be explaining problem number 8. If you want to see it or if you want to read it, you have the packet, deal with it. So you start with, initially you have kinetic and energy and potential energy due to gravity, and you have in the final you have potential energy due to gravity. And so I crossed out the masses because you can, makes it a little simpler. And then you just work through the problem. You have your gravities, you have your heights. And then I went and subtracted these to get this 15.9. Then I divided by the half, and then I squared it, I square rooted it. So the final answer. Yeah. All right. So this one is number 9. It's kind of a doozy because I had like a limited amount of space, so I have to explain a few things. So this is your first equation. This is the thing you start out with. It's the FD cosine theta is equal to KF plus UGF minus KI plus UGI. And so I simplify this down a lot into this next step. So what you had was the coefficient of friction force normal, but the force normal is equal to the force weight in this equation, so you can just say mg. d cosine theta is equal to 1/2 mv squared because it only has kinetic energy initially, and that's all it has. So then you plug in your numbers. You have your coefficient of kinetic friction. Oh, and you also cross out the m's. Make it simple. So you have your coefficient of friction. You have your gravity. You have your angle at which it's going, and you have your velocity. So this simplifies down. You do the maths. You do the maths. This negative 3.79 d is equal to negative 4.12, and then that solves to 1.09 meters for the distance.